We've got our second lesson of Unit 6 here. It is about converting between polar and rectangular forms within the same point for an equation. So I guess to start off, we're going to look at this this graph, if you will, over here on the right-hand side. What we've got is, if you could imagine this point, we have our origin, no matter whether we're talking rectangular, polar. We have an axis with an origin, and when we look at this point here, I'll turn it red for a minute. When we look at that point, we can look at that in two different lights. If we look at that coordinate in the polar system, that point, in order to get to this point, we went out to some radius r. Okay, we went out to some radius r by going at some angle theta. So we would define that work point, or that point here, as r comma theta. But in the same light, we have that same point. We're not going to change anything about the point, but we're going to look at it instead from more of a rectangular coordinate system. Okay, like this. So then, that same exact point we have in rectangular coordinates as over in the x, up in the y. So what we want to do is be able to take one system and convert to the other. So in order to do that, let's find the relationship between one system and the other. And the system relationship can be looked at through trigonometry. If we look at angle theta, and we are assuming that is a right angle there, we can say that, I'll do it over here, sine theta is equal to opposite over hypotenuse, so y over r. In the same regard, cosine of theta is adjacent over hypotenuse, or x over r. Now when we look at that, we've got a relationship now between the two different coordinate systems. We have theta and r related to our x's and y's. So what we can do with that is we can define y by itself. So, like, in other words, get y by itself or get x by itself. And in order to do that, we multiply both sides of each equation by r. So y is set equal to r times, see if I can get that a little better, there we go, sine theta. In the same regard, x is equal to r times cosine of theta. So if we wanted to find the conversion of given a polar coordinate, and we want to find out what x and y are equal to, we can just take the r and the theta that we were given and convert them to the x and the y's using these two equations. So I could even put them out here. Here's our conversion factor. Oh, cosine, sorry. I wanted to put my x first, and then I forgot to put my cosine first. So there you have it. That's where we get these equations. I didn't want to just throw them at you and say, here, use these. I want you to understand why they are, or where they came from. So here's an example. We now have the polar coordinate 2, 7 pi over 6. So in order to get our x, y, we say that that is the same as r cosine of theta. Well, r is 2, so 2 times cosine of our theta. Theta is 7 pi over 6. And the y coordinate is r sine of 7 pi over 6. 6. And at this point, I mean, you could leave them here if it does ask to simplify that, and I would. This does actually come out to about, because 7 pi over 6 cosines in the pi over 6's are square root 3's over 2, so that's negative 1.73. But sine in the 7 pi over 6, those are increments of halves, and that is negative 1. Double checking that, let's see, what coordinate, what quadrant are we in? And that is, let's see, 7 pi over 6, so there's pi over 6, there's 6 pi over 6's straight across. So we're in quadrant 3. Quadrant 3, cosine is negative, and so is sine. So there you have example 1. Then the second one for this, there we go. Same thing, we're just going to say xy is equal, xy is the same as r cosine theta, so 4 times cosine of pi over 6, comma, 4 sine over 6. Now we know pi over 6, that is in the first quadrant, so we should get two positive numbers. In fact, that comes out to be approximately 3.46 in the x. And sine in the pi over 6's, those were increments of 2 or halves, so that was just 4 divided by 2. And again, we can check that should be in the first quadrant. Both were positive, so things are looking good. I will pause the video here. This is a good spot to stop and transition, because that is going one direction. That's going from polar to rectangular. The next thing we're going to cover is converting the other way from rectangular to polar, which it's not any more difficult. It's just the math gets a little bit longer, but it's the same idea, just we're kind of working backwards. So